see. I think this is the microphone.
This meeting is being recorded. So
Yeah, you might get rid of that.
yeah.
Okay, so welcome to today's astrobiology seminar. Today's speaker is Stephane Mazavet from the what's commonly called the Nice Observatory, or the Observatoire de la Côte d'Azur, which is basically the observatory of the French Riviera. Not a bad place to be. And let's see, Stephane did his PhD at Australia National University in Canberra. And then after that, he spent about 10 years in the United States, ending up at Los Alamos National Lab. And he moved back to France, worked for the Atomic Commission Agency, and then moved from there to the Observatoire de Paris for a number of years. And then most recently, since 2021, has been the director of the Nice Observatory. Is here because he's currently visiting the University of Arizona, which made it easy for us to fly him here rather than all the way from France. But thank you so much for coming. And he's been doing some interesting work about habitability of icy moons and exoplanets. Thank you.
All right. Thank you, Dave.
Yeah.
So thank you for having me. It's been a very intense day, and I really enjoy my visit here, especially because most of the work I'm going to talk about is largely inspired of all the work that Dave and his group has done over the year. So it's nice to be giving a seminar on what we've done with all the great work that has been done here. So I wasn't sure what kind of presentation I could make because astrobiology community is pretty wide. Sometimes you have chemists, sometimes you have biologists. So I tried to set up a quick presentation to give you an overview of the various applications we've been interested in the past few years in trying to apply that coupling between planetary modeling and ecosystem modeling that comes from biology. So the main goal of the work is to try to couple both, to try to be able to describe at the same level the planetary environment, the biological activity, and the feedback of the biological activity on the environment. And we tried that idea a few years back with Régis Ferrière and applied it to a few systems, a few test cases in the solar system and beyond. So that's what I'm going to try to give you a quick overview today. Of course, doesn't work. That's what we didn't try. Okay, let's do that. So of course, when you talk about habitability, especially in the exoplanet context, we talked about habitable zone, that kind of properties that we have around stars that are not planetary properties. Sometimes people tend to think that habitability is a planetary property, and right now, from an astrophysical viewpoint, it's just a stellar property. That means for a given star type, you are going to have planets that are at the right distance where you can find liquid water at the surface, and you find liquid water at the surface mainly because you have a good timing between the stellar luminosity, the right atmosphere, so you have the right climate, and you can sustain ability like that. So this is a typical graph that you see. So that's roughly all the planets, exoplanets that are detected so far, where you have on the y-axis, you have the stellar mass. On the x-axis, you have the distance to the star, various ways of detecting exoplanet, various techniques, bias in those techniques. And you have that, what I put it in yellow, that kind of region around that stars, where hopefully, if the planet has the right atmosphere, it could be thought of as habitable. And of course, so what we call habitable planet in that context is we just take the planet that have been detected so far, mostly indirectly during radial velocity or transit method. So you have mean density, and you plot the planet that you have in that particular distance to the star that we call the habitable zone. And what we are finding at the moment is if you look at Earth-like planet, and the definition of what is an Earth-like planet depends more or less on who you are talking to. But roughly, if you consider that a planet that is roughly below 5 times the mass of the Earth and below a radius of 1.5 the radius of the Earth, you can find right now about 24 planets that are currently detected and that are in the habitable zone. That means they are potential target for further investigation to know whether or not they are habitable planets. You can expand that range if you start to say, okay, habitable or Earth-like planet is something a bit larger. It could be up to 10 times the size of the Earth, radius a bit larger. It could be habitable planet. You end up to a number of about 60 to 70 planets. So the current status right now regarding habitable planets is we think there is a distance to the star where with the right atmosphere, and that's mostly ideas that we get from the solar system. So if they have the right atmosphere, right distance to the stars, they could have liquid water, and they may be more or less looking like the Earth. In fact, habitable planet, what you see is you have a continuum between Earth, super Earth, and ocean planet, because when you start increasing your density, when you start increasing the mass and the radius at the same time, you are going to start increasing the mean density, decreasing the mean density, and you go from a continuum from super Earth to ocean planets. So one point to remember is right now, we don't have any confirmed candidates, so planets that resemble the Earth in terms of mean density around a star that resemble the Sun, the G-type star. That's what I put it here. Hopefully, that's what will be done later on with the Plateau mission, which is an ESA mission trying to characterize Earth-like planet around G-type stars. And so what people have been doing with that concept at the moment, so GWST, that's soon going to be renamed the TRAPPIST Observatory at the rate things are going. As I was hearing yesterday that there is 400 hours of observational time that was already granted for the TRAPPIST system. And what people have been currently doing, so TRAPPIST system that you know of is a brown dwarf, so very small star, and you have several planets that resemble to the Earth, mean density very close to the Earth, and among those, maybe 3 that will be in the habitable zone. So the idea is to try to confirm whether or not those planets are habitable, will be to get access to the atmosphere and try to figure out whether or not they do have the right atmospheric composition that would allow to have the proper greenhouse effect, to have those planets being able to sustain liquid water on the surface. And so what people have been doing, roughly to try to convince everybody that we should spend those 400 hours of observational time is to try to decouple the two. So on one hand, you identify density that resembles the Earth. And on the other hand, you try to mimic what kind of potential atmosphere it could be. So you vary the various pressure up to 10 bar of CO2, and you try to get some synthetic spectra of what those planet atmosphere could look like if they were habitable. So here I'm showing a case that was made for a community-wide initiative, so mostly to spend all the telescope time to try to characterize the atmosphere of the TRAPPIST planet. And that's a transit spectrum that would be observable if you had up to 10 bars of CO2 connected to the planet. And of course, you know, those 10 bars in a terrestrial planet are secondary atmosphere. So the atmosphere evolved throughout time with the planet, and you need to connect the two. You need to connect the evolution of the interior. That's a direct impact on the atmosphere, and the atmosphere is a direct consequence of the internal structure evolution. So right now, those two are more or less separated. And people think about characterizing habitability by just looking at those kind of spectrum, trying to detect whether you have the right amount of CO2, right amount of greenhouse gases that would give you surface temperature and characterize habitability. People keep on going on the same idea, saying, okay, we could put spectrum of primitive or modern Earth atmosphere and trying to identify beyond habitability inhabitation by looking at methane concentration and oxygen concentration and trying to guess how many transit you would need to be able to identify methane or even oxygen on those planets if they do exist. So that's what's done right now for GWST. And if you look at all the programs that are planned in terms of atmospheric characterization, you see that with the GWST, so we have our 3 or maybe 5 TRAPPIST objects. Maybe if we are lucky, we are going to find another system where you could do transit, and maybe GWST will be useful. But that's not with the GWST that we are going to be able to characterize habitability or even inhabitation. That means biosignature or biological activity. And if you look a little bit at the program, you see the Plateau mission I was talking about, the IL mission, those two are ESA mission, the ELT, and you have the GMT here in the US. That's where you are going to start. So at the end of the decades, you are going to start to be able to characterize atmosphere of planets resembling Earth-like planets, but you're not going to be able to do it around G-type stars. You start with less luminous star because you have a better contrast and you climb your way up. And it's really for the next generation of space telescopes. So beyond the ELT and GMT, it's really with the LUVOIR or those kind of dedicated space telescope that you can think of having enough object to characterize habitation or inhabitability or inhabitation. And so the question that is asked, and all the work we did is set into that context, is what kind of instrument do we need to build to really identify habitability and inhabitation? And essentially, it means what should we be looking for? Should we be looking at oxygen, at methane, at CO2, and those different gases require different instruments? And how do you interpret all those data? And so this is taken from one of Dave's review paper. I should have added, but I couldn't find the reference when I was putting the graph. But essentially, so what people have in mind is essentially to use Earth as a template in terms of trying to go beyond habitability and think about biosignature, is to look at the Earth history. And this is how you can summarize the Earth history in 3 graphs. That's what I like that paper, because you have on the left, so you see that in the Earth's history, you have oxygen that rose throughout the history of the Earth in 2 major steps. One step, so what we call the great oxidation event, but in fact, it's just a few % increase of oxygen in the atmosphere, so something that's not really detectable. And it's only in the past 800 to 900 million years that you have enough oxygen in the atmosphere to be detectable for an exoplanet. So if you're looking at oxygen as a biosignature, if you look at the Earth's history, maybe that's not your best bet, because there is no certainty that oxygen is going to rise, even if you have life on a planet. We have life on the planet way before the second oxidation event, so before it was detectable remotely. And on top of that, you have a lot of false positive. If you're entering greenhouse runaway, you are going to produce a lot of oxygen on your planet. So oxygen is maybe not the best gases, or not, maybe certainly not the only gases you should be looking for. So methane, you see, in the Earth's history, methane has probably varied a lot, especially when you didn't have much oxygen. So you had chemiotrophy and anoxygenic photosynthesis into play. But methane, so right now we don't have much physical constraint in the Earth's history, but on top of that, methane, just looking at methane, is not easy, or it's not easy to identify as a biosignature, because we know a lot of cases where you can have abiotic methane. Titan is a good example. You have a lot of methane into the atmosphere of Titan that doesn't tell you that there is life on Titan. And so that's kind of thinking about biosignature, what can come to mind and what the community is thinking of in terms of what gases should we be trying to detect. And if you look at habitability, I think another nice example, nice proof that the planet could be habitable is to look at the trend of CO2 throughout the Earth's history. You see that because we had the carbonate silicate cycle on the Earth, the variation, so the fact that the planet stay habitable for 4 billion years is connected to the fact that you had a carbonate silicate cycle. And if it exists on another planet, you should have a trend of PCO2 as a function of stellar luminosity. just to think one piece to go forward on the talk. So I'm talking about habitability. I started to talk about a little bit about biosignature and what could be useful to identify beyond habitability, what could be living or what kind of biological activity you could have on the planet. Simple view of life as a physicist is, if you look at, from my standpoint as a physicist, if you look at biology, you mostly have two main family of biological beasts. On the one hand, you have what's called chemiotrophy, so all the organisms that are living on chemical gradient and sustaining themselves on chemical gradient. And on the other hand, you have phototrophy, so you have a second big family where everything is driven by light, and that's how you produce energy. So what we focused our work is on chemiotrophy. So for two reasons. First, it's easier to modelize. And secondly, that's what appeared at the bottom of the tree of life, close to the thermophile and hyperthermophile. And so biologists debate whether photosynthesis started first or chemiotrophy started first, but it's a pretty good guess of having some simple organism developing on a planet just driven by chemical gradient and growing on chemical gradient. So if you put all that together, you see that the Earth's history as a template. You know, if you have your chemiotroph and your photosynthesis, you can see that O2 rise because you had oxygen photosynthesis. And the oxygen photosynthesis is a combination of two non-oxygenic photosynthesis. So maybe that's something not deterministic in terms of evolution of life on the planet. And it's likely it could stay without oxygen. And there is various arguments to go around that. First, because there is no correlation between the appearance of there is not a correspondence between the rise of oxygen in the atmosphere and the biological innovation. So clearly there is a coupling between the biological innovation and some geophysical processes that explain the rise of oxygen in the atmosphere. So maybe it's not deterministic. Second thing so you see the chemiotroph. So those species use oxygen and hydrogen. So that could be a good guess to look at in addition to O2, but also to look at methane and methane variation. And one thing that shows is when you have methane, which is also a greenhouse effect, is strongly coupled to the environment. So it's very hard to look separately, in our view, from the terrestrial or planetary condition and separate the influence of biology because you have a feedback between the two. So it's hard to look at just biology and planetary modeling, but we need to combine the two. Second point that we bring forward in that work is that you shouldn't look at the golden target approach. So sometimes people think we are going to detect one planet and that planet has all the properties that convince us that it's habitable and it's inhabited. We go with the idea that you instead need to look at trends in a set of exoplanets. And I think discovery regarding habitation, habitability or inhabitation are going to be convincing once you see that as trends in population of exoplanets rather than the property of a single planet. So when you put all that together, so the approach we decided to take with Régis Ferrière, with a biologist a few years back, is instead of doing what you have here on the left that I've been talking so far, so you look at the planetary condition, you try to guess either for habitability or inhabitation, what kind of ingredient you could get within an atmosphere to decide if it's habitable or inhabited, is to try to couple the two. So instead of having kind of an independent assessment of the various composition that would be into your atmosphere, what we set up ourselves to do is to couple the two systems. So you take your atmospheric composition, you make your biological system working, and we can do that because there is great progress that was done in ecosystem modeling now. So you can really simulate chemiotroph, as I was telling you before, and then you can get the feedback because you have full coupling between the two. So you can get the feedback of your biological activity into your atmospheric composition, a little bit like the oxygen. That's a feedback of the biological activity into your atmospheric composition. So that's the kind of things we are trying to achieve here. And three application I'm going to tell you about, where we applied that couple method. So trying to go beyond just the assessment of habitability and inhabitation independently, or just looking at some simple compound. So try to use that integrated method on three cases that we felt was relevant is Enceladus, because Enceladus simple system, there is some Cassini data that measure composition of the plume, and to try to decide whether or not we have biological activity or whether biological activity can help explain what kind of data. Early Earth, because there is a lot of data on early Earth, a lot of work that has been done, and whether or not we could see for early Earth and even early Mars some impact of the biological activity on the biosphere. And finally, because that's the main goal of the study, is to try to apply that to habitable planet and try to find biosignature from what I've shown you before. That means a few spectroscopic atmosphere, a few atmosphere characterized spectroscopically so far, but the necessity to try to think of what's the next, what kind of instrument do we need to build to identify signature, biosignature, or atmospheric composition that will show you that indeed those planets are habitable. So first case of Enceladus. So don't know if you remember, but the Cassini mission went to measure the Enceladus small moon of Saturn, and Cassini probe went through those plume and detected and characterized the various jets coming out of Enceladus. And what they found is CO2. So in those jets, you had CO2, H2, and CH4. And the case of Enceladus, I think, is really what we have typically in our field when we try to decide whether or not it's habitable, is for the same argument, for the same composition. People were saying, because you have H2, that's a sign that you have biological activity, because indeed you have methanogens use H2 to drive. So maybe you have biological activity. Other group of people with the same measurement of H2 were saying, you don't have biological activity, because they would have eaten up all the H2. So the fact that you can find H2 in those plumes is a sign that you don't have biological activity. And the way we approach the problem is simulate the two. So if you put the biological activity, then we can get the real feedback on the environment and decide from the concentration whether or not it makes sense to have habitability. One thing to keep in mind is for Enceladus, the way it works. So you have tidal dissipation. So you have water getting through a porous core, and through the process of symphotronization, you can produce H2 and methane. So what we do in those models, so that's a typical example. So that's methanogens. The methanogens, they are just using, you see, that's the kind of reaction. You're using hydrogen and CO2, and you're producing methane and some water. Okay, so that's what the bug is doing. Typically, the way we solve those problems, so just to give you a sense of those dynamical population. So here in B, you have the average cellular biomass. So what you simulate is population of cells that are going to consume various gases that you have on the left here, produce other gases that you have on the right. Okay, and X here, so that's the typical differential equation you solve, where X, that's the concentration of the relevant species. So you have a differential equation for each of those species. And here you have a forcing term that comes from your environment. So in the case of Enceladus, that's the ocean composition. If we are going to switch later on to atmosphere, that's going to be the atmosphere. And you see that with that activity here, biological activity that you're finding here in this term, you are changing the composition of either your atmosphere or the jet. Okay, so that's the concentration of a given species due to the environment and the biological activity. Okay, that goes a little beyond just looking at the free energy of a reaction and decide whether or not this is working for a particular problem. Second thing you do is you can look at, so when we do those kind of model, what we do is we look like species. So we are looking for, to know, we are trying to find whether or not life that, as we know it on Earth exists on other systems. And in that case, so what we do, you parameterize the property of the various cell to what is done here in the laboratory. So you can parameterize the efficiency of the metabolism and the energy that's consumed from what is currently known. And that's, so for the case of Enceladus, we took that particular bug, and you see you can have those nice graphs. People are doing some nice experiment, plug that into your differential equation. And what you do, in fact, is you ask the question that's on the right here. What you do is you do all that in a Bayesian framework. So you have modeling of your Enceladus, where you have a crust, an ocean, interaction of the ocean with the porous rocks. So you have rate of serpentinization that you can get from the literature. So you have an idea of how much hydrogen, how much methane production you could get. You can put methanogens living at the ocean core interface. So with those differential equations, you see they are going to change the amount of either H2, CH4 produced or consumed. So that's the balance between the two. And then on the right, so you got various prior. This is the CH4 escape into the plume. You do your modeling of how you create the plume from the ocean. And what we found is the following. So you have here in blue. So in blue, that's clearly inhabitable. So that means for with those biological model, because you have a population, so you couple that, so you're going to reach a steady state for a given condition. And that means non-habitable in those cases is you cannot sustain a population of those bugs I showed you in the graph before. Then you have what we call abiotic habitable. That means that's the condition where you could have those populations sustained for a while. And then you have what we call the biotic in the prior. That means once you have the biology feeding back into the environment, that you are going to change the H2 and CH4 balance with the biological activity. And that's what you identify as a detectable biological activity. And what was very convincing, so it's nice when you do all that work and you have, this is one of your first results you see on the right. In purple, that's the Cassidy measurement of the CH4 escape, and I can show you the H2, and you see that the only CH4 concentration that can be that's compatible with the data. If you're just considering production of methane on H2 by serpentinization, you have either the blue or you have the blue result, and you see that's not compatible with the Cassini data. So what we are seeing in that paper, we are not saying we found life on Enceladus. What we are saying is when you're considering serpentinization that give you a rate of methane and CH4, you cannot recover the Cassini data. When you put biological activity, you recover the right ratio between the H2 and CH4 that's detected into the plume. So two solutions, and that's what I think is nice with those methods, because you can quantify exactly what type of activity you can have, is to say, A, are we missing a process, an abiotic process? So maybe the core of Enceladus is much more methane. So that could change the balance between H2 and methane. So clearly, maybe we are missing an abiotic process. So people need to work and think about having the right abiotic process that gives you the right escape of methane. Or maybe there is indeed some biological activity, but then we can think of, and that's what we did in a following paper, we can think of traces or other elements that we could detect to see whether or not there is indeed a biological activity. So you see, I think that's the strength of those methods. It allows you to approach that question of habitability and biosignature from a quantitative standpoint and decide from that to go to the next experiment and think about the next observation, or in that case, the missing process that we may have regarding whether serpentization or the core of Enceladus. So, that was our first application. We kept on going, being more ambitious, saying, okay, we are going to do the full shebang now and couple the atmospheric modeling. So that's what you have in blue. And there we do a photochemical model and a 1D climate model. Essentially, what we do is we fix the mixing ratio. So we do grid of calculation where we fix the mixing ratio. We get flux at the boundary out of it. We do 1D climate model. We use all the to get an idea of outgassing and weathering. We couple that to the model of Joshua that's sitting over there. That was a great inspiration for that work. So we couple that photochemical climate model to the parameterization of the carbonate silicate cycle. And with all those ingredients, so that allows you to have, you have your atmosphere with various species, H2, CO2. So that's the grid. You can run the carbonate silicate cycle to see where you are in equilibrium with the atmosphere. So it's compatible. So you have the carbonate silicate cycle compatible with the atmosphere. And on top of that, we add up a loop with the ecosystem modeling that I was showing you before that's going to live in the ocean. So to just get you, put in the ocean in red. So the atmosphere is in blue and the ocean is in red. And in grid, you have the ecosystem developing into the ocean that's going to change the flux at the interface between the ocean and the atmosphere and see how that ecosystem, mostly chemiotrophy, impacts the atmosphere. So there, we started to do primitive Earth. So you see that's an ecosystem that's a bit more complicated because for Enceladus, we just took bugs that were using methane and using H2 and producing methane. Here, we do something more complicated. We have a full ecosystem like you have on Earth with methanogens, methanotrophs, so consuming, producing methane, acetogen, acetotrophs, so various reactions. And we simulated so the primitive Earth with those constants. So considering that you have 75% of the current subluminosity, initial abiotic temperature, volcanic outgassing, which is important because the volcanic outgassing puts H2 into the atmosphere. So that's something that's used by its biology. Did the climate model with those details, carbon cycle I just talked about, and the ecosystem modeling. So that changed roughly the CO2, CH4, and hydrogen concentration. So that has an impact on temperature. So that's how it modifies. So that's how the biology is modifying the carbonate silicate cycle through the temperature that acts on the weathering. So that's how you get your full system. So you couple all of those, and then you get steady states. Sometimes you get steady states, sometimes you don't get steady states. So what we found, several things that were actually useful to, I think, to go forward is first, you can play around. What I was worried when we started those methods, especially with the case of Enceladus, is that your results are very dependent on the bugs you are considering and on the fact that you have, if you take one given methanogen, you're going to get one result. If you take another one, you're going to get another result. So you can feel that it's not a stable situation. So for the primitive Earth, because we had data, we play around with all those parameters. So first, we consider an ecosystem that becoming more and more complex. So that's what you have on the left. So we start from the abiotic and we say methanogen appear first. Then, because in your calculation, you reach an equilibrium. Then you add up the methanogen plus the acetogen. So then you get another equilibrium. And we reverse all those different combinations to see if we ended up with a different product at the end once we have complexified the ecosystem. And second thing, so this is the result that we have on the right. So one thing we found was that each time you introduce biology, you do change your atmospheric composition. That's what you see here. I plotted the CO over CH4 ratio into your atmosphere. So you start from abiotic, so that's the log scale on the y-axis. And you see that you are changing. Indeed, if you start with metanogen, you are going to change that ratio. If you start with acetogen, you change the other ratio. But what's pretty interesting is when you start increasing the complexity of your system, you kind of reach, you converge your simulation. You see pretty fast, you're reaching a CO over CH4 ratio, disregarding of the complexity of your ecosystem and independent of the timing where you put that into your simulation. Second interesting thing is very little temperature variation between those various ecosystems. So if you start with simple metanogen acetotrope or very complicated, you see that your temperature roughly end up being the same. And what we found, in fact, is two things regarding coupling of biology to the atmospheric evolution. Is one, on short time scale, you do change the atmospheric composition. You can destabilize the climate, and probably, we played with shutting down the metanogens, like would have a major planetary impact or a major change in the geophysical environment. And if you kill the metanogens, you do run into snowball events. That's maybe what happened during the Uranian glaciation when oxygen appeared on the Earth and all the metanogen dies. So on short time scale, the biology do change your atmospheric composition, but on long time scale, that's pretty interesting. It's mitigated by the carbonate silicate cycle. So the Earth, when you put biology and you change the biology, is going to oscillate for a while, and then it's kind of stabilized due to the carbonate silicate cycle. So first result is we do see, even for chemiotrophs that are pretty low metabolism, we see significant impact on the atmospheric composition. Second thing we played with is with Monte Carlo simulation. We did thousands of simulations to vary all the biological parameters, and you find, in fact, that you have pretty clear trend, rather independent of the precise details of the biology you put it in. So you can change the catabolic energy, so all those parameters that define a given species, you can play around with them, and it doesn't have much impact, so you can do trends of the impact on the atmosphere. So what we found is, indeed, when you're considering a planet that's known, but it's better when you quantify it, that as soon as you have biological activity, is going to shape the atmosphere. And despite all what people were saying regarding, you had all those ideas about the Gaian hypothesis and whether or not life can drive Earth out of equilibrium, we found that life did shape the Earth, but did not make it habitable or not habitable. In fact, the two are pretty, Earth is pretty stable regarding biological activity. And so we kept on going. You see, when you have a hammer, you start to see nails everywhere. So we kept on going, saying, okay, let's keep on trying that model for early Mars. And early Mars, people are interested to send rover to Mars because maybe we think that Mars was pretty similar to what Earth was like 4 billion years ago, because it didn't have tectonic and reshuffling of the surface. Maybe we can find clues of what happened early on in the history of the Earth. So we went on to try to model early Mars with metanogens. And what we're finding, and putting you here, the take-home message is, while on Earth, we found that metanogens and chemiotrophic activity tend to stabilize the climate. On Mars, it did completely the opposite. If we did have metanogenic activity on Mars, it quickly drive Mars out of habitability. So how does it work? So evidence for Mars being habitable, that's something you all know of. When we just look at the surface, we see geomorphic feature that clearly indicate that we had water, liquid water on the surface of Mars. It goes beyond that. We found clays, so we found all kind of proof that shows that we had liquid water running on Mars early on. To make Mars habitable is not that easy, because Mars is much further out than the Earth from the sun. And 4 billion years ago, the sun was 25% of its current luminosity. And if you just take an atmosphere made of water and CO2, you don't have enough greenhouse effect to make Mars habitable. Even if you crank up the CO2 into your atmosphere, you cannot make it habitable. One idea that came up a few years back by the group of Jim Casting and student Ramirez is to try to adapt. So it was an old idea going around, but got the problem solved using some hydrogen into the strong CO2 background. And in fact, this three-body collision between the hydrogen and the CO2 that makes an absorption and make it back an efficient greenhouse gases. So solution to get Mars habitable, one of the solutions, and we don't know if it's the right one, but one of the solutions to make Mars habitable 4 billion years ago is to have a strong between 5 and about 5 to 10% H2 concentration into a CO2 atmosphere of overall a few bars. And its initial idea, I wrote it down, that was Sagan had in the 70s, in 77, talked about it, but didn't have the CI collision, so the calculation never worked. And all that work turned around having a better evaluation of those cross sections, so get a better idea of how hydrogen behave in a dense CO2 background. So did the same, played the same game. This time, we put it the biology differently because we didn't consider a full ocean. We consider bugs that could live in brines, so that means highly salty water, so and stuck into the porous regolith. And same thing, you know, so it's an ecosystem, H2-based methanogen that live in saline brines up to temperature down to 250 Kelvin. So the geophysical model, essentially, so you have a gas exchange between the atmosphere and the crust. If you freeze on the surface, you know, you are going to block the exchange between the continental crust and the atmosphere, and that's going to depend on the freezing point of the brine. You know, if there is some unknown, it's between 200 and 273 K. So how, and it depends roughly on the salt concentration into your brine. And so the biological model is pretty simple. It's a depth structure model. So you have your bugs living into the crust, and depending on the surface temperatures, they're going to get closer to the surface, or if the surface is cold, they are going to get deeper into the mountain. So this is the kind of 3 scenarios, and I see that I had a movie at some point, but I don't have time to read it. So you have 3 scenarios where you start always with those initial conditions, 3 different melting temperature for your brine. You put the methanogen to run, so they are going to suck up. In fact, what they do is they are going to suck up the hydrogen. Okay, so if you are sucking up the hydrogen, then you are going to drive Mars of habitability. Yeah, I've got that movie. I can show you. Okay, it's running. You see, so as the biology starts, you are starting to remove the hydrogen from the atmosphere, and then you are going to freeze the surface and cut the exchange between the atmosphere and the ground. So, in fact, that project started not to be looking at that. The project started because, you know, we are looking at mission planning on various surfaces of Mars, and the question, you know, people like the ExoMars, you know, they want to dig a few centimeters into the dirt to try to find some leftover fossil biomass. And so we started those calculations to say, okay, does that make sense to dig only 2 centimeters? How can we be sure that biology is not at 20 kilometers? So we're trying to estimate at what depth would be the highest biomass fossil left from the potential activity on the surface of Mars. And the question was, okay, does that make sense to dig? How should we dig? Where should we dig? And how deep should we dig? So result that we got was Mars is indeed habitable. So that's what I showed you previously. Fact that you have H2 consumption, you have decrease of the surface temperature, so you drive Mars out of habitability. If you have low freezing point for the brine, you have no ice, you have a larger feedback, so you again got a lower surface temperature, and then your metanogen gets deeper. So overall, we found that, yes, we can have metanogen living on Mars, but unfortunately, after a few 100 million years, it's going to soak up all the hydrogen of the atmosphere and then take the planet out of habitability. More importantly, is you see, depending on the freezing point of the brine, because we are not too sure about those compositions, depending on the freezing point, probably you need to be digging much deeper than a few centimeters. And of course, you can do 3D mapping of potential climate on Mars, and you see you have sites that have the best condition between surface temperature, and because the hotter is your surface and the closer to the surface are going to become the bergs, and so left over some potential fossils. And you see we can characterize like that sites where you have higher probability of finding biomass. And little kick to that story is you look at ExoMars, because in that context we started that work. So ExoMars that decided to go to Oxia Plenum to dig. And from our simulation, that's the worst place to go if you had indeed metanogen in the crust of Mars. And if Mars was habitable, that's not where we should be going. Going to Hellas Planitia is the highest rate of finding something if something ever occurs on Mars. So, okay, so that's another example. Last example, I've got a few minutes left. So you see, we've done application coupling that planetary modeling, so biological activity. We started with Enceladus. You don't have atmosphere. You have a simple planetary environment. We could say something or quantify potential activity and trying to see biosignature. We look on primitive Earth to see the impact on the atmosphere. And you see you have the impact. And I showed you that throughout the various ecosystems, you kind of have convergence of composition within your atmosphere that could be seen as biosignature. Because if you look at the CO to CH4 ratio, you see that it tends to something disregarding of the complexity of your ecosystem. So you potentially have a biosignature. We also, with the primitive Earth, convince ourselves that the result is not that dependent on the details of the biology that we are putting into the model. And on early Mars, we saw that not only we can quantify the impact for the early Earth, so seeing change in composition, but also finding for early Mars that the feedback of the biological activity in some cases can indeed change what we call habitability. So biology, depending on the context, on Earth, Earth seems to be resilient regarding biological activity, despite the fact that its atmosphere is modified. On Mars, which is the case, I mean, it's habitable because it has a lot of hydrogen, so it's a kind of little exotic. We see that biological activity can indeed drive the planet out of habitability. So what we set up to do is what can we learn from exoplanets? So we took that model from primitive Earth and generalized it for exoplanets. So you can run thousands of simulations. So here you have what I showed you before regarding the ecosystem modeling, and in red, you see that's all the parameters that you can vary. You can vary the pH, the CO2, the flux, or changing the stellar type, or just the evolution of the luminosity throughout time. You can change the volcanism as a function of time, because you have a planet that evolves, so the volcanic activity evolves as a function of time. You can change the erosion, that depends on temperature. So you can really generalize the Earth's history and try to set up yourself to say, okay, what kind of trend should we detect in population of exoplanets that look like Earth, so kind of Earth equivalent around G-type stars, and generalize the simulation. So that's what we did. So we did the full 4 gigayear evolution with metanogens, and that's each point. So what you're seeing on the right, each time simulations. So each point is a simulation where we have our atmospheric grid. We couple that to our carbonate silicate cycle, and then we have the biology running into the simulation. So each point shows a quasi steady state between the planetary modeling, so the atmosphere, the carbonate silicate cycle, and the biological activity. And typically what we get is those kind of graph where, for example, on the first, on top, the top line is the PCO2, then you have the methane pressure as a function of temperature, CH4, so typical matrix, and here you have temperature. And so what you are seeing is exactly what I was showing you at the beginning of the talk. When you look at Earth's history, if you're just looking at the CO2, for example, variation of PCO2 as a function of age. So you could put it also as a function of luminosity, because the sun luminosity varied for 4 billion years. So you put it as a function of age. You can see that what we call habitable, so the habitable conditions are going to correspond to a decrease of the CO2 concentration as a function of time. When you take, so the black dots, that includes the yellow dots, that what we call habitable planet, in the sense that you have surface temperature where you can have liquid water as a surface. What we call habitable for methanogens is within those habitable conditions in the astrophysical sense. Those are the conditions where we can have a sustained population of methanogens. That's the orange dot. And the green dot, that's the impact. So it's feeding back into the methanogenic activity is feeding back into the atmospheric composition, is feeding back into the temperature. So in green, what you have is a steady state. Okay? So now, when you're looking at the PCO2, CH4, or temperature as a function of age, you can ask yourself, okay, what kind of instrument do I need to try to decide whether or not I can recover this kind of trend? Looking at the Earth's history, you have a long-term carbonate silicate cycle. That's what I showed you before. We had a decrease of PCO2 as a function of time on Earth. If all habitable planets do have tectonic and a similar carbonate silicate cycle, they should display that trend. And so that's what we've been playing with the simulation and trying to, so that's with the group of Daniel Apai in Arizona. He has an ICAR grant to try to design the next generation of telescope. So we use is Bioverse simulation. So what Bioverse does is it takes the probability of finding Earth-like planet around G-type stars and the possibility of detecting them with a given telescope configuration to be able to do spectroscopic characterization. And you see that if you take the Luvoir A configuration, so your findings I'm putting on the right here as a function of age, the number of planets that you expect to be detecting, and that expectation is based on extrapolation of the Kepler data. So it's extrapolating the yield of Earth-like planet around G-type stars. And you see that even if you build Luvoir A configuration, you are going to find, if you restrict your definition of habitable planet as something very close to the Earth in terms of mean density, if you're lucky, you can get 8 planets, so 8 G-type stars, 8 Earth-like planets around G-type stars. Not much to be able to identify whether or not we have the trend in CO2. If you enlarge, as I showed you before, what we call Earth-like planet and extend it to larger planet and lower densities, you can increase to up to 15 planets around G-type stars, but then you're entering another set of problems to decide, you know, if you have twice the amount of water on the planet or different ratio between iron silicate and water, are we going to have the same kind of carbonate silicate cycle? So here, it's not obvious we're going to show that. But it's just to give you an idea that once you do those kind of simulation, you can start guiding and having ideas of what should be, how many planets or what's the population of exoplanets we can expect, and is that enough to see trend in CO2? Is that enough to see trend in CH4? And going to show you, because we went a little further, so we got the carbonate silicate cycle that was parameterized here. And so we played around deciding, we know between the Earth and Venus, you have two different, on Earth, we have the tectonics, and we believe that that's the tectonic that allows us to stay habitable for 4 billion years. And we're not too sure. I mean, there is debates regarding the fact that Venus ever had tectonic and why we have tectonic on Earth and we don't have tectonic on Venus. So you have a stagnant lead mode. So we really did all those kind of simulation, not only using, so tweaking the parameterization of the carbonate silicate cycle that Joshua had done to remove weathering, changing the outgassing rate to have it more. So we have one for the tectonic regime and one for the stagnant lead regime that you can parameterize as a function of the volume of magma that you produce. And instead, so it's just a follow-up study following the paper that we did here with Lemmer, where we're trying to decide how many planets do I need to be able to see that you do have correlation between the PCO2 and the luminosity of a planet. I think in that paper, you came up with a number of 85. You need to identify 85 planets to be able to see whether or not tectonic is something you're finding on a large, whether or not tectonic is what you're finding on every terrestrial planet. And instead, we reframe the question, instead of comparing behavior of CO2 for tectonic like for a planet that experience tectonic against a uniform CO2 background, is to compare two different regimes. So there we compare a tectonic activity against a stagnant lead. So we have two different trends of CO2, and we feel that 25 planets would be enough to distinguish or be able to decide whether tectonic is something that's a property of terrestrial planet, or, you know, or maybe it's more a stagnant lead. So that's the kind of study you can start pushing to try to decide what kind of instrument we can put forward for the next generation of telescope. And that's under review, and I should give you a copy because that would make sense. That's what I was telling Joshua, that he lands on your desk for the review. So maybe we should talk about it. So I think I'm on time. So habitable planet, clearly that's a concept that we need to validate in the coming decades. Biosignature is a concept that lacks some firm basis. Everybody has his own view regarding biosignature. What we are trying to do is to develop a new approach where you can couple so the photochemical, climate, ecosystem modeling, and interior modeling. We did the first few demonstrators and the first few applications on Enceladus, early Mars, early Earth, Earth-like planet around G-type stars. And so we are expanding that work, of course, trying to include now photosynthesis and get different coupling between the atmosphere and the interior model. And I'm already showing you a few examples that comparing stagnant lead and planet with tectonic activity. And we can think about also expanding that to ocean planet and those kind of things. That's it.
So questions?
Yes.
I think that this work is super interesting, and I'm very fascinated by it. Have you considered, in addition to trying to improve this, pulling in some other kinds of chemosynthesis? So things like sulfur oxidizers, and then there's sort of sulfate-reducing bacteria to do the opposite side of thing, or something like that, like other biological.
Yes. So I'm not the biologist on the team, but that's what Antona was doing his thesis with us, and Boris was doing a postdoc with us. That's what they are looking at right now. So I mean, the idea, you see, you have a framework, and it can be expanded in different ways, you know. But so putting, when you have sulfur, you can think about putting some sulfur based metabolites that seem to be pretty relevant. So yes, everything is there to do that.
Josh?
Yeah, thanks so much for the interesting talk. It's really cool to see all these applications of the ecosystem model back to back. You briefly mentioned for Enceladus, you had some follow-up work on other species that could be detected that might help distinguish between the biology model or some other source of abiotic.
Yeah.
I'm just curious.
Yeah, in fact, so what Antonio did following this work is he tried to expand to quantify how many complex molecules on which quantity you could get, from a metabolism that you have more complex and macromolecules that are produced. So he tried to do a cleaner job in terms of evaluating the biomass that's produced, and from that biomass, what kind of a chemical tracer you could recover from. So that's the idea. So, I mean, essentially is to say, well, let's just not look at hydrogen and methane ratio, and let's push on other species that are, like glycine and all those kind of things. Things that we associate with, you could think about DNA, but that would be ambitious, I think. So it's more like complex chemistry, a step forward. Yes.
Lucas?
You mentioned that for the, I guess, in the school earlier model, approach of trying different orders, which the different metabolites.
Yes. Yeah.
Combinations. I'm just wondering if you also took the approach of like the available energy, the sequence of available energy for the metabolisms. Some they wouldn't arise.
That plays a role. Yeah, yeah. That plays a role, but I think that's why it works to be self-consistent. It doesn't matter, because if you take a population that needs to feed massively on the production of another population, is going to stay there, sitting until the other population. So if you have, for example, acetogens, they're going to wait until you have the acetotroph or methanotroph that comes into play to start growing. So I think that's why at the end, that's the steady state that counts, not necessarily the trajectory, because they are interconnected. So that's the.
Okay, any other questions? If not, let's thank Stephane again.
Thank you.
Thank you.